So yeah, welcome to Mark and Luca. Both of them are PhD students at ETH Zurich, working in the SRI lab, a group that I think traditionally has looked at formal methods in machine learning, as well as the intersection of programming languages and machine learning and language models. Today, they're going to talk about a language that they've been developing called LMQL for large language models for prompting for constraint decoding. And I like this language very much. It sort of is a general kind of solution to a lot of the decomposed types of modeling problems that our team has traditionally looked at. And as a funny kind of side story, I hope I got this right, but I think at iClear last year, during Tushar's decomposed prompting poster, I think Mark came up to him and wrote out an on-the-fly program in their language about how you can implement decomposed prompting using LMQL.
I did this at multiple NLP, LLM posters. Wearing a T-shirt, ask me about LMQL. I did this at ICLR and ICML. I think this was at ICLR though.
Yeah. So that seems to be your thing. That's quite cool. So we're very happy to have you here, so you can tell us more about it. I'll pass it over to you guys, and as we discussed, we have an hour block, but we like to have discussion. So I guess the normal routine, people can interrupt during the talk as well. So I'll pass it over. Thank you.
Yeah, thank you so much, Kyle. I'm Luca. I'm a PhD student at ETH. I'm here together today with Mark, and we're going to speak a bit about LMQL. It started as a research project, and now it's an open source project. And put in one sentence, it's a programming language for large language models. I hope I will be able to communicate a bit what that even means in the next hour. You can just ask questions at any point in time. I'm totally open to interrupt whenever something comes up. So LMQL is originally it was a research paper at PLDI actually. I'm the first author, but this is obviously joint work together with Mark and also our supervisor, Martin. It's also an open source project now, so you can check it out on GitHub. And we have a little community that actually helps us a lot also in learning about what people actually want from a programming language in the space. Very important aspect, I think. Before we get into the details of what LMQL is, maybe I can give you a bit of a timeline of since when we are working on this and how it sort of evolved since then. So actually we started working in summer 22 on this. Like quite literally our Professor Martin asked us to look into language models and programming languages, and that's all we got. So we started to sit down and look a bit at the space, and we were doing a lot of programming language work before and traditionally did a lot of research there. And we started to look at prompting and how people were using language models at the time and how these prompting, I guess, algorithms kind of work or like what's the computational model behind all of this. And is this even maybe some kind of programming? And based on this, we built LMQL as sort of this query language to actually implement those kind of computations. And once we finished the first implementation of LMQL, we actually went to NeurIPS that year in New Orleans. And I think that week ChatGPT came out, and it was like, okay, wow, this thing is really taking off. Like this is quite a bit better than what we've known before. And we just had finished working on this. And then after this, things got very turbulent, but also very exciting, of course. Like this whole space exploded. At some point, we went open source and got lots of feedback and also positive attention in that sense. And since then we did several follow-up works also in different areas, like in a more applied area, like in chatbot development, for instance. But we also did a lot of work on special kind of decoding algorithms that make sense in this setting. And then now our most recent work is actually something we put on archive in February, which is called Domino, which is project that's more focused on the performance aspects of making constraint decoding basically overhead free or even better, like negative overhead, while also maintaining sort of this minimal invasiveness. I'll talk mostly about sort of the original LMQL and also what you find today on GitHub. And then towards the end, I hopefully can tell you a bit also about Domino and also kind of what it means and highlight maybe some other interesting works as well.
Just as a brief interruption, feel free to interrupt Luca with questions like I'm just doing.
Yeah, please. All right. So some motivation before we get into inventing yet another programming language. So programming with large language models, why would this make sense? So the lens we look at this is kind of this idea, okay, we have language models. They are like this magic text-to-text function that can do all sorts of computation as long as you just ask for it. And it can do many things that traditionally were really hard, quite well, zero shot. So you just have to ask for it, like chatting and question answering, code generation or classification, like all sorts of different tasks are quite nice to implement if you call it that. But the question is a bit, okay, on top of these sort of new form of text computers, text functions, can we use them as building blocks somehow and program with them in some more structured way, or construct some system that behaves maybe on a high level more like an algorithm, but on a low level embraces LLMs? And our response and also sort of the idea we mainly pushed in the original paper is, yes, we think it is kind of a form of programming. Obviously, if you worked a bit with LLMs, there are some rules that are being broken here, like they don't behave quite like a deterministic computer program functions would, but still it's kind of a way of programming with them. All right, so maybe to get on one level here, so that prompting is programming. That's sort of the fundamental thesis. And we obviously all, like, ever since ChatGPT, many people have had like this experience of sort of going forth and back with a chat language model. And there's like this forth and back interaction. You ask for something, the model does something, it's probably wrong. Then you asked it to correct itself, and then sometimes this works out. And this is on the one level, like this is kind of the most amazing part about LLMs, right? On the other hand, it's also like programming, right? You're giving instructions to a computer to do something, and then the computer sometimes at least does it. But also, of course, in the standard flow, there are some issues, right? Fundamentally, LLMs are still magic boxes. So you can prompt all day long, and in the end, on some samples, it will still not work. So there's no ultimate control like there would be in regular programming. This makes them also quite hard to automate, right? If you use an LLM as part of a traditional computer program, you can't rely that the LLM will always respond in a specific format. So it's kind of, there's a sort of a broken interface between the two. So what's typically done is there's a human in the loop, and when the LLM gives me this lengthy explanation for what I asked for, the human can just read this and understand what it actually means and what the final answer really is. If a computer does this in a traditional sense, it's much harder to extract this. And this sort of interface is kind of not very robust in that sense, right? What you typically want is some kind of very specific JSON format, or maybe some structured format, like maybe some tree or something. And then in the end, there's also the efficiency aspect. The very best models we have today are still very expensive to operate. So every request you send out is kind of has financial or computational implications at least. And obviously you want to kind of optimize this a bit. So on the efficiency side, which is something programming languages historically have been really good at, also there's sort of this need to optimize a bit. So what we propose is this idea of, okay, instead of having human in the loop doing the forth and back, like this doesn't really scale, this is like kind of brittle and very human focused. Let's write a program that goes forth and back with an LLM. And in this case of LMQL, this program is not just going forth and back, but it's actually also much more controlling on how the language model responds and what kind of format it can respond, like templating and constraining its output. And this enables this idea of, okay, we write a program and the program actually runs with the language model to together kind of compute some final result. So LMQL looks like this an example of an LMQL program. The general idea is you use something like a scripting language like Python in our case and combine this with natural language prompting. And it looks a bit like here on the right. So you have, on the one hand, natural language text, but on the other hand, also well-defined control flow and programming statements. What makes this possible in the end, because we're kind of interweaving code and language model output, is that we actually constrain the model during execution. So it cannot just answer anything, but we actually strictly constrain the model by masking its output distribution to only produce outputs that have very specific structure, at least in terms of their output format, like a JSON object or a number or a true-false label. And this sort of combination of a language makes it actually quite easy to implement, like classification or even some more advanced applications like a looping thing that calls tools, like what people would call an agent that kind of acts autonomously and tries to come to some reach some goal in the end. Yeah. At the same time, we kind of formalize this idea of how these forth and backs with a language model look like, these algorithms on top of LLMs, and having them written down in a program actually also gives us opportunity to optimize this. So we actually see what's coming in the program and we can sort of prefetch this during execution, do some smart caching, and also by constraining, just lowering the general number of times you have to query the model. Maybe to sort of give you a high level, where do I put this? Like it seems to be two things, right? We have on our one hand, we have language models. They are very, like have the soft way of reasoning, like there are these text computers. And then on the other hand, we have traditional programming. It's like this very discrete, well-defined type of reasoning, very algorithmic, very reliable, like really good at doing math, but also not really good at, I mean, you can't implement sentiment analysis with a few if statements probably, or not a very good one at least. And LMQL kind of lies at this, in the top right of this spectrum, right? It's both, it's interweaving traditional programming and prompting, and it's sort of a form of hybrid computation of trying to combine the best of two worlds. All right, so I will try to convey a bit what LMQL is, or how it works, and how you could use it, how you would use it, and what the computational model is, a bit by going over some use cases. But before this, maybe a bit of an overview of what makes this, what is LMQL even in components, and like there's different layers. There's sort of this, we have implemented it, it's a runtime, and we support different kind of models that you can use in the LMQL style. And then there's like a concrete feature set, like we support the templating and the constraining of models to make this form of lockstep computation possible, which on the highest level enables you things to like tool augmentation or modularizing the kind of code you want to run. So LMQL is really just Python. It's quite literally a superset. So if you know Python, you can already write valid LMQL code. But the catch is, or the bonus feature here is, you always have an LLM during execution right in line. It's like a first-class citizen in the language. So we can do some computations, A plus B is C, and print this. But we can also at any time, like here in line 7, just ask an LLM about some value that we currently hold in the program state. So we can just ask about some fun fact about C, right? And the way this is done is by these top-level strings. And then there's this placeholder details in this case, which indicates that the LLM will sort of complete this part of our template that we provide. And then once we execute this statement, we actually have the value of details right with us. Like, it's like a standard statement in an imperative programming language, right? So this is one of the aspects. It's first-class citizen. But also, as we execute more code, we can again ask the LLM, okay, what about half that? And it's not like each statement is a new request to an LLM starting from a clean slate. Actually, we are kind of, we're staying in the same context window, right? So if we now ask, what about half that? The LLM sees that previously we asked about 4 and what it responded, and now it can see, okay, we're asking about half that, and it can actually relate to this kind of context it already has. So that's sort of the underlying sort of addition of on top of a standard imperative language. And what does this enable us already? So let's say we have, like here we had simple prompt statements, right? But we can actually have prompt statements with multiple placeholders. So you could do something like this. You could ask for, or you can ask for a summary of Bruno Mars the singer, and then provide a template, for instance here, structured like a JSON object of a shape that you actually can determine. So that's set in stone. This will be adhered to, and only the placeholders will be completed by the model. So here on the right, you can see how this is completed, and also how string values are actually completed as strings, and integer values are actually completed as integer values. So this enables templating in that sense. Here, it's really just used to generate a JSON object, but you can also template entire reasoning processes, like first do a list of pro cons and then do some reasoning on top of this, right? So it's a much more involved process of sketching out exactly what the LLM will respond or how it will respond, versus just letting it do whatever it thinks is best or whatever the distribution says. Yeah, please, there's a question, I think.
Yeah, I have a clarification on the previous slide. Very interesting. How do you, it looks as if the conversation or the response is in like a continued context format, like where the previous queries are still being stored. Can you also like clear the previous context and start a new, like, so to say, like inference query?
Yeah, so this is sort of the way you do this in LMQL is by implementing functions, and each function has its own context. So by calling a function that would be on its own another query, LMQL query like this, starting from a clean slate, you could do this, take the result of that and insert it into your current context window, like here, for instance.
I missed that detail. Okay, so you actually are feeding back in the LM's previous response as new context to the second.
In this case, in this case, in line 12, the context window will already include the prompt from line 7 and the response the model gave for the placeholder details, right? So it's already the sum of all that, or the concatenation of all that. So it keeps track of what you asked before. Only if you call a function, sort of it starts in a separate, fresh context. But by default, it's all the same context.
Okay, thanks. Very cool. I have a question on the next slide as well, which is about when you query the model. So if the user provides this, I guess, structured format, do you optimize the natural language query to be like a string format, and then you just return the model's output in this format, or are you actually querying the model with the same structure? Because it might be like suboptimal, right, to ask models to complete these fields in this specified structure as opposed to like a next token completion.
So
suboptimal due to what? To the tokenization, or due to maybe the choices you make in ordering the attributes or the white space?
Just like to be most similar, right, to the observed data at training time, I guess.
So the way we infer the placeholders is we step left to right through the template. So actually, it's an auto-regressive completion process. So actually, indeed, like if you, depending on how you decode this, but if you decode this greedily, the model will not see that there will be a field age later on when it predicts the value for name, right? And we go left to right through this template and complete like this. The only difference to standard autoregressive text generation is that at some point we transition back into template where the model cannot freely choose what to produce, but we actually force the template until the next placeholder occurs, right?
Okay, thanks. So the program on the left is the actual input query to the model, like but you do segment it based on like what you're attempting to complete, essentially.
Exactly, yeah.
Okay,
so there's no, this is actually, like we don't convert in the background something to a different prompt or something. Like we always try to take what you give us and directly force this during coding. On top of this, you could have prompting layers, but yeah.
Okay, thanks.
So presumably you have to be quite aware then when you write these prompts that it should be sort of left to right interpretable. Because even when you do constraint decoding, if you're doing constraint decoding on super low probability tokens, it's probably not going to be a very good output. So you probably have to be quite mindful that it's sort of a humanly meaningful thing to actually go left to right and then know what comes next. And you're not indicating to for the int value, for instance, you're not indicating to the model in any way that you want an integer. I guess you could have said age underscore integer or something in the key, and that would be more of a signal that I want an integer.
So if you use LMQL, all the things you say you want to do this, like greedy constraining is not enough, because if the model doesn't know that it's about to be constrained to only produce numbers, bad things could happen. Like the distribution could be set up in a bad way that you really go into some subspace that's so high perplexity that nothing reasonable comes out of the model. So in practice, actually, you do want to prompt and constrain. So you do condition the model to produce the output you expect, but you also enforce it strictly that it actually does it. And I guess from a language perspective, that's kind of, LMQL is lower level in the sense, right? You can still do the prompting yourself, but we don't add some magic prompt behind the scenes, because this actually makes things very intransparent in practice. But I guess, yeah, on a higher level concepts, people could build on top of this and sort of come up with some prompt that also conditions the model. But then again, prompt engineering and even automated prompt tuning is still very much an open research problem. Like, what's the best prompt even?
But do you try, when you do constraint decoding, do you try to keep track of the probabilities? So if you're constraint decoding, and it's like, oh my gosh, I am constrained to an integer now, I have to go way down the token list to do like token choice number 10 million with probability 10 to the minus 10. That should be sort of a warning flag, almost like a compiler warning or a runtime warning that this program of yours might not do what you expect it to do.
So we do have different decoding algorithms on top of program semantics. So you can do greedy, you can do argmax, you can do beam or best k, or even some custom ones we created. And some of these decoders actually check this. Like, I mean, in beam search, typically you wouldn't even go down that path if it's actually that low probability. But if you're constrained to a subspace that's only so little of the probability mass is left that all tokens will basically be bad choices, at some point the decoder will actually warn you and say, actually, I'm going down a really dark path here. Maybe consider this when interpreting the answer for sure. But yeah, it's sort of constraining doesn't protect you from getting into these cases where actually you're operating in some very low probability space.
Right. Cool.
And just to Olivia's question there, just to make sure I'm understanding. So when it generates the age, it doesn't have any full warning that it should generate an integer. You're just hoping that it will guess that an integer is likely to be needed based on that keyword. Is that right?
Yes. So we do constrain, but it could be that what we constrain to basically is probability 0, right? And then you're just sampling random numbers at some point, of course. But typically you do constraining and combine it with few-shot samples where the model is demonstrated, the format, for instance.
And similarly, in this example, you have 2 top songs, so the system doesn't know ahead of time that it's only expecting to generate 2 top songs. Is that
exactly
right?
Yeah. But then if you do, like, we have sketch-aware decoders implemented that kind of it's beam search, but it's bucketed by where you add in this template. And then sometimes you can sort of see, okay, if we additionally consider the probability of ending the template here, or like the next deterministic part of the template, maybe the sequence probability goes way down, and then you can know, okay, actually this is not a good song choice at this position, and we have to backtrack to a different hypothesis. But yeah, I mean, beam search is just an approximation of backtracking. Full backtracking obviously is very expensive.
Thanks.
2 small addendums. What might be slightly confusing in the slide is we just say that there is an int value and a string value, but we don't actually anywhere constrain the model. You need to have an int here, you need to have a string. That was abbreviated for brevity. We'll get into that later. But really we know, okay, here we accept the string, so that's really any model output, and here we accept an int, so this is only the subset of completely numeric tokens, which then results in a Python integer primitive.
Yeah, that's actually the next slide, so I can.
Yeah. And the other addendum is like most of the semantics Luca mentioned so far are for the standard decoders. That means greedy, argmax, or standard sampling decoder. As you mentioned, we have custom decoders that are aware of like the further variables, but the user can also describe their own decoder, and there you could do things like I'm expecting an object with strings and integers. Age is an integer, and then you would get this like as your magic pre-prompt before seeing the real output. So you could always write something like this using LMQL. Back to you, Luca.
Yeah, so as Mark mentioned, the constraints are actually not shown here, but it's a key thing. Like the constraining obviously needs to happen. And to show this a bit, let's look at a simple example again with an A and an B, and let's ask the model to compute the result here, which is typically a bad idea actually in this simple case. But what will happen in an unconstrained case, like if you just generate a response to this with possibly an instruction-tuned LLM, it will, for instance, in this case, respond with new line, 2 + 3 = 5. And that's obviously in a chat context a perfectly viable response. Like a human will read this and they will understand 5 is the final answer here. But ultimately, if we don't have a human here, because this program runs in an automated system, we actually just end up with a string of several characters and some numbers in there, but it's not clear what actually the result is. And this is still a string, like we still haven't gotten an integer out of this. And what's typically done in this case is people come up with heuristics to, like they check for the last number in the response, and then this may be a number or not, and then they try to cast this into an integer. All in all, it's like, it's not a very reliable process. And what you can do in LMQL is you can just specify these constraints. And these were omitted in the last slide, but what you do is you add this where clause to this prompt statement, and you specify a constraint like, for instance, integer c. And this means 2 things. When the model, one thing is when the model generates these tokens for this placeholder, it can only choose from the smaller next token distribution, where we only allow tokens that are actually valid numbers or parts of valid numbers. And then once it actually produces this value, we can actually be sure that will always be an integer because we forced it to only choose digits. So the result will always be an integer, and thereby we can also always convert this automatically to an integer, meaning in line 6, when we actually access this, it will be of type integer, not some string that we need now to post-process or something like this. So it's, yeah.
Sorry. So in this case, could you end up with the answer 2? Because if you look on the left, the first number I see is 2.
Indeed, this is one again of the cases where naive constraint decoding is not enough, because when the model is forced to produce an integer number, it is not. It can't anticipate that this will be the last number it will have generated, because it might have had plans to add +3 equals 5. What you actually want to score in this case is this number plus end of sequence token to sort of score actually if this is a full response, because 2 plus end of sequence tokens in this case would score quite low, because a sequence couldn't end there because the model sort of is conditioned to complete this into 2 plus 3 equals 5. Doing this in general, however, is quite expensive, because this would mean you would have to backtrack again after having seen with the end of sequence tokens that 2 alone cannot be a good choice here.
Got it.
So typically this is solved by small width beam search. Typically works out, because you can just you will get the long and the short answer in the top few tokens, and then you can identify quite quickly if you complete this to end of sequence what will be the correct response. All right, so how do these constraints work? You cannot just specify integer, but we actually support a small logic-based language that gives you control over length of things or stopping phrases on what phrase a placeholder should actually be stopped being decoded. We also support regular expression constraints, and also we support conjunction and disjunction of all these kind of constraints. So we can actually derive sort of a logic-based language. And we translate those into token masks that at each inference step, when the next token is predicted, is invoked to determine what even would be a valid token in the next step. So here you have a little animation showing this. When the model predicts the next token, we consider the constraints and remove those tokens that would violate the property, and then only choose from the remaining allowed tokens. And the way we define the semantics of this as logic-based language is actually ensures that we never rule out a token that would violate our constraints and would not violate our constraints. So we kind of minimally invasive in the sense that we will not rule out and paths that could still lead to a valid answer. All right. So what is this useful for? How is this used in practice? So one thing that people really like to do is using constraining to build classifiers from LLMs. And one common task, for instance, let's say we are some data scientists working at a travel booking website, and we have to analyze the sentiment of some reviews people left. And we could just use prompting for this. So let's do that. We show the model in this prompt statement the review, and we ask the model about the sentiment of this review. And then we actually do sort of a two-step computation. The first is we just ask the model to analyze, and that's like fully whatever it wants to produce. There's no constraints on this placeholder, so it produces just some free text analysis. Could be seen as kind of a latent reasoning variable. And then after this, because this analysis to us in code is not useful, we can't directly from this extract, is this a positive review, a neutral, a negative review? Maybe we have other labels. But we can now use in a second step constraining to actually say, okay, based on the analysis you just made, what's the overall sentiment? And then we can constrain to, for instance, positive, neutral, negative, forcing the model to choose from these. Now again, to come back to this point before, the model at the point where it predicts this classification hasn't been conditioned that the labels would be positive, neutral, or negative. What's common is to just say, okay, from the choices positive, neutral, negative, the overall sentiment is, and then do the constraining, so the model actually is conditioned in a way to sort of focus its probability mass on these tokens anyway. So one way would be to use constraining, and then we can just we can be sure in the following context that the value of classification will be positive, neutral, or negative. But we can also even get more information because we can extract token scores. And there's a custom keyword for this in LMQL where you use distribution instead of where. And it's like where, it forces the model to choose from a tree, but it actually extracts distribution over all possible labels. And it does this by looking at the scores of the possible options and then renormalizes them into a distribution or something at least that sums up to 1. And in this case, we can see the score is very much focused on one label being positive here. And this gives you, I guess, some kind of scoring mechanism. I know, obviously, there's lots of work on this, that maybe this token distribution cannot be directly interpreted as confidence in that sense, because there's many cases where this is not always a given. But in practice, like, people use it like this, and in practice, this can actually at least give you some hint at what kind of classification was made here. So, for instance, if all scores would be about the same, then you probably would want to maybe even not do any classification at all, because maybe it's too low confidence, or it's basically random what kind of label you would assign. So all this model, having the model in line with your code, templating, constraining, and extracting distributions, this is kind of the core language of LMQL. And since it's a superset of Python, it also seamlessly integrates. So you can just use LMQL in your Python program. You write some query that is some kind of prompting flow with constraining or measuring distributions. And then you just call it like a function. So you don't have to think about setting up the APIs or concatenate the prompts yourself. You just write this function and you call it anywhere in your code and sort of get, for instance, your classifier or your analysis engine, whatever you implement in the end with a query like this. So that's sort of the operational layer: templating, constraining, distributions. And we also have some support on the compositional layer, so the sort of this idea of also organizing your code not in the small but in the large. So one thing is tool augmentation. So let's have a look at like some simple object tracking tasks. This is like from a LLM benchmark. And these questions, I mean, maybe you all know them, but there's always like a story and people are exchanging objects. And then at the end, the LLM is asked to guess or to tell us about what color ball does Alice have in the end, or something like this. So it's ultimately about state tracking, about building up this internal model of who owns what, and then kind of in the end mapping this correctly. Now, traditionally, LLMs can be quite bad at this. I mean, if they do in-context reasoning, things can get messy. If they mess up once, it's already over, probably. But actually, computers are really good at doing this kind of state tracking, right? So tool augmentation sort of can help us here in this case, because we can sort of combine the best of both worlds. So for instance, let's just implement a simple key value storage, top right here. It's basically a Python dictionary, right? And then on the top bottom right, we actually not just let the LLM reason, but we structure the LLM reasoning very strictly. So we say, you have like we few shot it to actually demonstrate this kind of format of reasoning. And then we ask the LLM to use these tools, assign and get, as it reasons. And whenever it actually starts to evaluate this code itself, because LLMs will just hallucinate the evaluation result of a tool, we actually stop it at that point by constraining, evaluate ourselves, insert the actual tool output, and then continue reasoning. So the output will look something like this, where colored text is actually completed by the model and non-colored text is actually inserted by our control logic. And here we always actually do the evaluation ourselves in the control logic, whereas the LLM sort of does the step-by-step reasoning. And we can see the LLM actually uses this assign function. It has been demonstrated to do this before, but then in the sample it also does. And whenever it does so, we actually execute ourselves. And then in the end, it actually also uses the get function to kind of determine with the help of tools the final result of the object that Alice has in the end after all the swapping. And I guess in this case, it does answer it correctly. Now, of course, there's still opportunity to mess up. Like maybe it hallucinates the wrong tool call, but sort of the memorizing of what it decides each transaction to mean, this is actually handled by traditional program code, and this will always be up to cosmic rays, I guess, always be reliable at least. So that's an example of sort of very close tool use. Another thing that we looked a bit into is modularization. Again, borrowing sort of from traditional programming language design. And what we've looked at here is kind of, okay, we have these prompts now. Sometimes they have multiple placeholders, multiple parts and steps. And then we do something like this, for instance, where we ask for the birthdays of different people and then ask the language model to compare them. And it does it, but it's kind of all over the place. And we start, okay, maybe those this output format of the birthdays, I don't like this. I want this to be very specific. So let's just prompt the model. Maybe constraining is not even needed. Put in like these instructions that it always responds in this very specific date format, and it does this. But kind of looking at the prompt now, it's all over the place, right? And if this was code, this would be just code duplication because we have to write the same code over and over. And the idea here is to say, okay, typically what helps against code duplication is with refactoring or modularization of code. And the way we support this is by saying, okay, we support the notion of nested queries. And previously I said you can have functions that start from a fresh context, and nested queries are essentially functions, but that are executed within the context of the current inference call. So here we define this inline instruction basically to respond in a specific format as a function. And whenever we actually generate the answers, we insert those instructions locally only for this value, instruct the LLM to respond in this format. And then once it did, we actually remove the instructions again from the context. So it's kind of, if you know how function calling in low-level computer systems work, it's very similar. Like it operates on some stack, it runs some instructions, it produces some result, and then it removes its own context again from the stack, leaving only the return value. And that's very much a similar design. A bit more experimental, I would say, for sure, but it ultimately lets you like reduce the need for repeated instructions, and it also means when we decode the final answer, the instructions for generating some previous answers are no longer in context, and we can actually save on some tokens, as those instructions will not be needed anymore anyway. All right, so that's kind of the, let's say, current state of the language. I hope I could give you some taste of what it is or how it operates. You can also just try it out yourself. I invite you to do it. and play around, so you can see a bit. Now at the end here, I want to give a bit more of an outlook, also what we want to do, and maybe what others in the field have been doing. Like, this has been actually a very active field of research, it seems. And I want to structure this into parts. One, constraining. I think this is sort of its own kind of field, and then the other, more this programming aspect of programming languages and language models and how this works. So constraining and grammars is one field, I would say. Grammars, because traditionally grammars have been the format of how to define a format, and like the output format of an LLM, grammar-guided generation, code can be defined, or the syntax of code can typically be defined to large parts as context-free grammar. And based on this, there's a number of interesting works. So for instance, I think Synchromesh was one of the very first works that identified this mismatch of language models having this really weird and messy vocabulary, where there's subword tokens that sometimes like arbitrarily sized chunks of words. And this is in heavy misalignment with the tokens of a programming language, for instance. So the most troublesome part about this is if a token in the language model vocabulary actually spans multiple terminals of a parser of a formal language, which makes the parser state tracking and constraining actually quite involved. And as a result of this, many like naive approaches don't implement this correctly, meaning they actually restrict the set of tokens the model can use in constraint decoding too much, because they don't account for all those interesting transition tokens, and those happen to be quite important sometimes. So one aspect here is you can do constraining the wrong way, and if you do, it's overly invasive, and it's like it disturbs the model in a way that it has not seen during training, and that can be quite troublesome for downstream task accuracy, can disturb the model in many ways. An interesting aspect of this has also been observed with the guidance tools. It's like a Microsoft templating language also for language models. And they observed that if you prompt the model the wrong way and you sort of end on the wrong word, where typically this word and the next token the model predicts would have been merged in training, then this ends up in really bad tokenization, which will be very out of distribution to the model. And this can actually heavily affect what the model outputs, even though on the text level, everything may look the same. But on a subtoken level, it actually gets quite messy and complicated and very high perplexity. And then another interesting trend, or I'd say important development, is in this rise of pre-computation. Mostly a performance question, but actually, if you do high performance model inference, you want to be as fast as possible, and to take constraining should not take up any time in the token generation loop at all. And I think outlines was the very first to do this for regular expressions, and it's quite effective for sure, and also obviously helps adoption of constraining. And based on this kind of our more recent work called Domino, is this idea of being minimally invasive, but also pre-computing this for actually full context-free grammars and parser grammars, and making this really fast, even faster than unconstrained generation. Because if you know the structure of the output, so you sometimes speculatively at least can get ahead of the model and actually save some time and be faster than regular generation would be. So yeah, and I invite you to check that out as well. Our sort of midterm plans are actually to turn this into the next sort of backend or version of LMQL that's actually much more, basically overhead free in a way, which is currently not the case yet. And then I guess to close this a bit, the question is a bit, okay, we have grammar-guided generation, and it's actually a really nice formal construct grammars and a good background to have anyway. And in some cases, like code generation and schema-driven JSON generation, like the thing everyone wants to do these days, it's actually really good fit. But the question is a bit, are they the ultimate answer, right? Because grammars are not the ultimate programming model, I think. They're sometimes a bit counterintuitive. And people that just want to do some simple multi-part prompting, or have like, sometimes they have constraints, but sometimes they don't have any constraints at all. To them, it's actually quite cumbersome to write grammars. And so the question is a bit on a programming model avenue, I would say, what's the next step here, and how to, what is the way to program language models? I think LMQL is a draft and kind of a playground also to experiment with some ways of doing it. And I would say a very imperative way. But there's obviously many different ways to do it. And I think many different things to be explored here. I want to highlight maybe two projects, other projects here also, like Microsoft put out AICI, which is like this idea of having an interface to make this constraining and these front-end languages easy to build, because they do a lot of the back-end stuff, similar to LLVM in traditional compilers. So I think that is a really cool development in the space, because it makes building these kind of languages much easier, at least as long as you do some kind of constraining. And then obviously things like VLLM have been also really helpful in sort of consolidating all this performance tuning that's going on all the time into some inference backend there. Maybe as the last bottom line here, obviously there's many others in this field, and I think everyone's trying to find the right abstractions, and that's obviously also cool to see. Many try to build sort of the everything framework. They seem to want to build an all-encompassing thing. I'm not sure if this is the right approach, but like DSPY, for instance, has also been really cool to see, like how they think about modularization, for instance, or like bigger composite systems. So yeah, looking forward also to what they come up with. Yeah, so I can only please I invite you to check out the website, and we have like a playground if you want to run it and inspect what's going on behind the scenes also. And then this part I'm happy to answer any questions, and together with Mark that may have come up.
Great, thank you. That was a wonderful talk. I would say we give a round of applause, but it's a bit awkward with the virtual. Are there any big questions? We have 5 minutes left for questions.
I had a quick question. So, can LMQL be used with closed models like GPT, where you don't have access to the decoder?
Yeah, so we have OpenAI Model Access, and it's one of the more popular choices. Not the most. The most obviously is like full access models, but you can do it, like at least with the completion APIs they provide, because they actually allow biasing of the distribution. And doing it at every step becomes expensive, but actually you don't need to do it at every step. You can do lots of speculative generation and only backtracking if things actually go wrong. And we could actually build a quite effective backend, I would say, even though they do not give us a lot of access to their models, for sure.
Right, thanks.
Quick question. So this is very interesting, and you have an example on the object swapping. I'm just curious about what's the scope of tasks that you have looked at for reasoning.
So we did actually a whole paper on how sketching this reasoning process, not with tools, but just with like the reasoning structure, like doing a list of steps or doing like a weighing of different sides. And this can help, but ultimately I would say the problem is it's like prompt engineering, right? Like you may have a good idea of how the model reasons best, but it's like ultimately hard to engineer it. It's like prompt engineering in that sense is already a difficult word because sometimes these models don't work the way we would expect them to work, right? And it's similar with like what tools even help the model and what kind of reasoning structure will even help the model. So there goes engineering, or like, I guess, just trying things into finding those programs, but then it can be helpful, yeah.
I know OpenAI has this response format as a JSON object, so that goes part of the way to getting. So that's what I do if I want to get a structured output. How does that compare with what you've done?
So I think there's JSON mode now in the modern APIs of OpenAI. So that's actually constraining. So they give you 100% guarantee that it will be valid JSON. I don't think they enforce schemas there yet. And then there's function calling, where they actually, as far as I know, just fine-tuned models on being in the right format, which is an approach to take, and I would say it's the OpenAI approach to take. But it's actually not 100% guaranteed. Like, models in this mode still hallucinate weird APIs that don't exist. And that's something that you, with constraining, you can actually solve for good. Like, there's no way the model responds in a way that doesn't fit your format.
I have a hybrid question. So the state tracking example where, you know, Alice has a ball and gives it to Bob and whatnot, is really interesting because you sort of show almost like a really explicit way of building a, not really a prompt, but kind of a half a prompt, half a piece of code in your system. And I'm assuming it does it really well, and that if you give it any sort of problem of that class, that you could do it really well, but it requires hard coding sort of that solution in your language, right? And so is there an intermediate hybrid approach where you could sort of give your language specifications to GPT-4 and get it to code a solution in your LMQL that it then executes, so that instead of having a solution for just a narrow class of problems, like that state tracking in exactly that format, you could sort of get it to build arbitrary solutions?
Yeah, so I guess there's two levels. Like, we got this question a lot because people were like, your language is great, but can you make GPT write it for me? which hurts me as a PL researcher. But I think I understand what you mean, in the sense of, here's a way of tools that you can use, now code a solution to use those tools and sort of interleave it with prompting. And what we found is, like, you can do this, like, it's even easy for the model to pick up LMQL, even though it hasn't seen loads of it, because it's so close to Python and also quite declarative. But I haven't, like, end-to-end evaluated this on many tasks. I mean, it's obviously a bigger undertaking also.
To add a bit, I have also at ICLR in front of people, because this question came up. What you can do is you can say the interpreter just has a loop and has access to the eval function, because we're still in Python. Yeah. So we can say, hey, LLM, come up with a function description. Then you can eval it, and then in subsequent calls, you can actually refer to the functions it just wrote. That works. That is horrible from a security research perspective. Half of me is a security researcher, so do not ever do that, please. But it works actually quite well. And there's actually an area of research called tool discovery, where if I have an agentic LLM agent, can I find tools and then use them? So nothing stops you from essentially implementing the patterns that people research with there in LMQL. And then you have the upside of executing the LLM and the tool in the same Python context. This might be something you want or something you don't want, but in general, it works quite well.
That's cool. Thanks.
I think we have to leave the room here now.
Yeah, we're out of time, but thanks again, guys. That was a great talk.